So the MO theory, we won't be getting to too much in the future. You don't have a lot of application to use MO and to study the organic chemical reactions. But more practical are the valence shell theory and the VSEPR theory in geometries. The VSEPR theory, it is basically the Lewis structure affected bond angle and geometry. And this, in your studying of the general chemistry, the first semester, you spend a lot of time doing some practice. So I go fairly quick on that. I won't spend too much time on that. If you're really rusty on this, you have to spend your own time to work on this topic. And so the central atom, the number of electron groups, which is either a bond or lone pair, and that affected the bond angle. And in this book, they use the steric number. The steric number means how many electron groups if you study general chemistry. So this compound has 4 electron groups, so that make it tetrahedral. 4 steric number is 4, or tetrahedral geometry. And this is ammonia molecule, have 1 lone pair, 3 bond. This lone pair count 1 electron groups. And so this steric number, or the number of electron groups, also 4. And water is also 4 because 2 lone pair, each one counts 1 group. And when there are hybridization, okay, the hybridization, we learned about in general chemistry, there is a correlation between the number of electron groups and the hybridization. When the number of electron groups is 4, you have hybridizations sp3. 3 electron groups on the central atom, that's the sp2 hybridization. 2 electron groups, which should give you linear, and that is sp hybridization. And so sp3 geometry should be ideally 109.5 degrees. When they are lone pair, if one of the electron groups is lone pair, the lone pair have more negative charge, it'll push the other bond a little further. So this bond, okay, between the lone pair and the bond, the angle is larger than 19.5. But this bond is invisible because we cannot really see the lone pair. But anyway, the outcome for this larger bond angle, it is make the other bond more squished, is less than 19.5. So the actual bond is less than 19.5. And in the water, there are 2 lone pairs, so the situation becomes worse. And the pushing is even stronger, the bond angle is even smaller. The actual observable bond angle is less than 19.5 degrees. So that's called sp3 hybridization. We won't be spending too much time on this. sp2 hybridization, the angle should be 120 degrees. This is the boron trifluoride. This is the trigonoplanar. And it's not octet, as you learned before. It's have only 6 valence electrons. And this is supposed to be practice, but if you look at this Lewis structure with lone pair and double bond, again, this is 3 electron groups. A double bond counts 1 group, and lone pair counts 1, single bond counts 1. 3 electron groups, that should be sp2 hybridization. And because this is lone pair, it pushes the other 2 bonds stronger, which will cause this bond angle a little bit less than 120 degrees. The geometry for this structure should be bent, as we know, because it's not linear. You have a 120 degree, nearly 120 degrees angle. And sp hybridization. The sp hybridization involves the 2 electron groups on the central atom. And the examples, we have a beryllium hydride. The beryllium is a group of 2 elements, have only 2 valence electrons. And when they form bond with the hydrogen, because the high electron activity of the beryllium, it forms actually a covalent bond between the hydrogen, which will make the beryllium have 2 electron groups, and that will make the sp hybridization. Bond angle is 120 degrees. Carbon dioxide, this is in our general chemistry, we did it many, many times. I think most of you guys remember the Lewis structure. And then this carbon have 2 double bonds. Each one comes 1 group. So I have 2 groups, linear, 180 degrees. And so that's the hybridization, both sp hybridization, because 2 electron groups. And so that's the correlation between the VSEPR theory and hybridization. VSEPR theory gives us the Lewis structure. And from Lewis structure, we see how many lone pairs, double bond, single bond, triple bond. Then we decide how many electron groups. And the electron groups will determine, it's the same as a steric number, it is the same as the number of electron groups. The Klein's book uses a different terminology, but it actually is the same as the number of electron groups in the general chemistry. Number of electron groups. That determines the hybridization. Molecular polarity. So this is a topic we talk many, many times in general chemistry. So I keep it very short. The electron activity, which is the capability of an atom to withhold, to attract electrons, it affects how the atoms share electrons. Either evenly or unequally shared, and which atom have more share of the bonding electrons, it depends on the electron activity difference. And electron activity in the organic chemistry, since we focus on the covalent bond, which is only involved in nonmetals, which is only the up right corner of about 10 nonmetal atoms. So the range is very small, and the discussion can be more focused. The force that for the atom to attract electrons, we call it induction force. Induction. It is basically how the nucleus positive charge attract the electron, especially the valence electrons. And those attractive force uneven share between 2 atoms, it causes the dipole moment. So for example, chlorine and carbon. Based on the electron activity, chlorine is more to the right in that row. And so that makes it the chlorine have higher electron activity than carbon. And because of the difference, the high electron activity, it pulls the electron harder. In the end, the electron shared is more toward the chlorine, which will make the chlorine slightly negative charge. And as a consequence, the carbon has slightly positive charge. So we have positive negative charge separation along the bond. It causes the dipole moment. At the dipole moment, the calculation in physics, it is the number of charge times the distance between the charge. And that causes dipole moment. We use this arrow to represent. The arrow is always from the positive charge, point to negative charge. So have a polar bond. And the how much bond polarity depends on the how much charge. We can actually discuss can you guys still hear me?
Yes.
Okay. Sorry, I think my I need to change.
Okay, so how polar is a bond? There's a qualitative way to measure. We're not use that for organic chemistry, but in experiment we can measure the dipole moment, and based on the dipole moment and bond length, there's a way to evaluate how polar or how ionic one bond is, and we call it ionic character. Because according to the electronegativity bonding theory, the difference between the covalent bond and ionic bond, it is not black and white. There's a progressively the percent of the bond behave like ionic or charge separation versus the charge electrons equally shared. You got a purely covalent bond. And so the way to, in physics, there's a way to calculate. You basically use the observed dipole moment and calculate how much charge on the atom, and use the calculated charge to calculate the ionic properties. And so you can see these are the three typical bonds in organic chemistry. You have the carbon oxygen single bond, OH single bond, and CO double bond. These three bonds we can measure the dipole moment, and also the bond length can be measured. Then with these three, with the dipole moment and the bond length, we can calculate the charge, and based on charge, we can calculate how much percent of the ionic character. And you can see the CO bond have only 10% ionic character, so it's very low. Even though there's charge separation, oxygen's high electron activity, it causes more negative charge and carbon positive. But the ionic character is only 10%. OH bond in organic chemistry is very common, it has 30%. Roughly 30% of ionic character. It's fairly high. Carbon oxygen double bond, because the oxygen form a pi bond. They share more and pull more electrons from the carbon. Ionic character is even higher. The bond polarity combination of the dipole moment and cause the molecular polarity. That was another very important topic in general chemistry, but here we just quickly review. So in here you can see this molecule have 4 bonds, and 2 bonds is carbon with a chlorine. The chlorine is being high electron negative. So these 2 bond dipole combined together, it'll give us overall a molecular dipole moment. Between carbon and hydrogen dipole was not shown because carbon and hydrogen have a similar, closer electron activity. So it causes it still have a dipole moment, but it's small enough. We don't consider that. And so the dipole moment combination, keep in mind, is not linear. You simply just add them together or simply just subtract. It depends on the angle. The next example about ammonia, the ammonia have a 3 bond, and each bond is fairly polar because the big electron activity between the difference between the hydrogen and nitrogen. That big difference causes 3 polar bonds. Those 3 polar bonds combined together will give you the combined dipole. This combined dipole is point up. So the ammonia is a very polar molecule. And in water molecule, the water have only 2 bonds, and both are polar bond. Because the bond angle is not 180 degrees, they will not cancel. So that will cause a polar molecule. Water molecule is actually fairly, very, very polar. In computational chemistry, there's a way to show you through the quantum mechanical calculation. You can calculate the electron density at each point around any molecule. And then when you consider the electron density and charge electrons, we can actually map how much positive charge in what area of the molecule. And that is what we call it the electrostatic potential maps. It basically shows you which molecules are more polar than others. Very, very neat looking because the color shows you the positive or negative charge. So when this this diagram, this is the legend shows you the more blue in the full spectrum from the red to violet. The more red is negative charge, more violet is positive charge. And you can see this molecule has only 4 atoms. One-sided molecule, because the chlorine is more negative charge, and the rest of the molecule, the charge has to be neutral. So if one part of the molecule is negative, then the rest will be positive charge. So the rest of the molecule give a positive charge. This map can be very helpful to understand how does organic molecules react. And so these are some dipole moments, shows you different molecules. Some molecules very polar. For example, the acetone is very polar, have one of the highest dipole moment. And you can see some other molecules, not so much. Water is fairly polar, 1.85 Dipole. Methanol is a little less because you have a CH3, which is fairly non-polar part in the molecule. And you can see that ammonia is very polar, and this is the organic molecule with no OH bond, have only oxygen, carbon, and carbon-hydrogen bond, carbon-carbon bond. So it's fairly low polarity. And getting to the a 5-carbon have only carbon-carbon single bond. This molecule is a 0 dipole, which means non-polar. And finally, the carbon tetrachloride is a symmetrical tetrahedral molecule and have 4 identical bonds. And that means all the dipole moment from each bond get cancel out. You have a non-polar, a 0 Dipole molecule, which is non-polar. And so how does those, for example, how does the pentane, this molecule, being non-polar? It has so many bonds. How do we know? If you draw the real molecular structure based on the real angle, you have 5 carbon, each one's a tetrahedral. And each carbon has 4 bonds. Those bonds are all roughly 109.5 degrees. So you can see each bond slightly polar. It looks very busy. But if you consider those dipoles can cancel. If the dipole moment are the same value and the opposite to each other, which means 180 degrees to each other, then they will cancel. So that means, for example, this bond and this bond would cancel. By the way, this is a wedge, this dash. Wedge and dash is one way to show the 3D structure. Wedge means close to me, and dash means away from us. So this bond will cancel. And likewise, this and this will cancel. So you can see all the bonds, when they pair up, they cancel out each other. And you can likewise see these 2 will cancel, these 2 will cancel, and let's see which one will cancel this. This, yeah. These 3, okay. These 3 will combine together, will give you this combined dipole. Okay. And these 3 also combined give you another dipole. So in the end, all the slightly polar bonds have this fairly small dipole all get cancelled. You have a combined and nonpolar molecule. So even big molecules, we can still consider how does dipole combine and decide if the molecule polar or nonpolar. Intermolecular force. In organic chemistry, this is one of the most important things in organic chemistry. How does molecules interact with each other? And because that will affect how does molecules react to each other. How does a organic molecule soluble? Is a compound soluble in specific solvent or not? It depends on the intermolecular force. Intermolecular force, we spend a lot of time in general chemistry, so I'll go fairly quick. It has the 3 forces if we are talking about a pure liquid. Okay, we're not dealing with the solution mixture yet. Only in the pure liquid, there will be up to 3 intermolecular force. The most basic, easy to understand are the dipole-dipole force between the 2 polar molecules. And the hydrogen bonding is actually the strongest among the 3 forces. Dispersion force, even though it's weak, it is actually exists between any 2 molecules. So that's the So first dipole-dipole is between the polar molecules. The polar molecules attract to each other. It's very similar to when the 2 magnets attract to each other, because south and north pole, they can attract to each other. And so for example, the acetone, we saw it is a fairly polar molecule and they attract to each other. The alignment goes, the negative charge oxygen orient or getting close to the positive charge of the carbon end in the another acetone. And this acetone has its own oxygen negative charge attract to the positive end of the carbon from a third acetone. So it's kind of like a, very similar to the magnets to attract to each other. And so the dipole-dipole force make it very strong. It causes stronger intermolecular force, and which will cause higher boiling point, higher melting point, and so forth. And so here's an example between the 2 molecules. These 2 actually looks very similar. Both have one carbon-carbon, one double bond, and have a 2 carbon-carbon single bond. And the acetone difference is it have oxygen instead of a CH2. So this is pretty much the only difference. And the molar mass is very similar, but you can see the physical properties fairly different. Melting point, acetone is much higher. Same as the boiling point is much higher. So the reason why does this one have a higher boiling point? Because they have a similar molar mass. So the dispersion force should be similar. But this molecule, you have a carbon-carbon bond. This is non-polar bond. Carbon-hydrogen is polar, but the polarity is very small because the difference between carbon and hydrogen is fairly small in terms of electron activity. So this molecule, if you compare between these 2, this is the only difference. This is a fairly weak polarity because the fact that it's have only 2 hydrogens. These are fairly weak bond. And this weak bond, as a matter of fact, it causes the dipole moment going toward the carbon. And so in the end, it's all these, the CH2 or CH3 polarity essentially cancel out. This molecule should be a fairly weak polarity because the other bond, this bond, all 3 combined together have a very weak dipole, go this way. These CH3 combined dipole, it is such. So you can see the each group of atoms combined dipole, they kind of point against each other. is collide to each other, cancel out each other. So this is a fairly essentially nonpolar. I'm pretty sure I have a very tiny dipole moment because between this part and the other two, but essentially it's very weakly polarity. But if you look at acetone, the CH3 give you dipole point this way. And the CH3, because the carbon have higher electron activity, combined dipole, it should go this way. But look this bond, CO double bond. Oxygen have high electron activity, so you have a very big dipole by itself this way. In the end, the combined dipole, it should be a large dipole moment, a very polar molecule. So you can see between these two molecules, which have a similar molar mass, similar dispersion force, but because of low polarity, this has a very weak dipole-dipole attraction, whereas the acetone have a very large attraction. So with all things considered together, the acetone should have a stronger intermolecular force, which explains why the boiling point and melting point is much higher. So that you can see the effect of a dipole moment cause the physical properties difference. Okay, hydrogen bonding. Everyone being familiar with hydrogen bonding have the nitrogen, oxygen, fluorine. Only these top three most electron negative atoms, when they form bond with hydrogen, such molecule or structure will have a very strong attraction to each other. And so this is how the water molecule form hydrogen bonding. The hydrogen bonding, even though it is essentially electrostatic, it is actually a very strong dipole-dipole attraction, but it's much stronger than just dipole-dipole. And it actually have an angle, specific angle. The consider hydrogen from one water molecule, this bond. Hydrogen will attract to the oxygen from another water molecule, but it's not attract to any location, any direction of the water molecule. It actually only attract to the lone pairs, the location of lone pairs in the water molecule. So remember, this oxygen have 4 electron groups. The bond angle is almost 190 degrees. And you have 2 lone pairs that is tetrahedral, in the tetrahedral direction of the oxygen. So only the angle between these two is very close to 190 degrees, even though the lone pair is invisible. Hydrogen bonding, it actually have a specific orientation, and it's very similar to the dipole-dipole interaction. Dipole-dipole interaction causes a specific direct orientation between two polar molecules, and same with the hydrogen bonding. And so for this water molecule can form another hydrogen bond with another water molecule. And you can see the alignment. Oxygen, hydrogen, lone pair, oxygen, they are supposed to line up to 180 degrees. Likewise with this. Oxygen, hydrogen, lone pair, and oxygen is essentially 180 degrees. It's not a random angle. It is fairly specific. And with this oxygen, will have 2 hydrogen bonding with the other hydrogens nearby. So this is a network. It's a network between the water molecules when they form hydrogen bonding. So that's water molecules form hydrogen bonding. Each water molecule can form 4 hydrogen bondings. 4 hydrogen bondings. The water molecule 4 hydrogen bondings. Ammonia molecules are very similar, but the the lineup is also very similar. Nitrogen, hydrogen, lone pair, nitrogen, that's one hydrogen bonding. And each ammonia molecule can also form the 4 hydrogen bondings. 4 hydrogen bonding. This lone pair on the nitrogen form hydrogen bond with the hydrogen of the other ammonia molecule, and so forth. And yeah, so when you have 2 organic molecules, this is the organic molecule. Organic molecule, carbon, oxygen, hydrogen form a hydrogen bonding like this. The compound capable of forming hydrogen bonding, we call them protic. Protic is the word come from proton. It is basically the it is implying such hydrogen, which is combined with oxygen, nitrogen, such organic compound. This hydrogen have a higher positive charge, almost behave like a proton. So we call it protic. Almost behave like a proton. The protic compound are capable of forming hydrogen bonding with themselves. Also can form hydrogen bonding with solvent such as water. So in organic chemistry, we look at those structures, and that will affect the chemical reaction and the water solubility. And so these are, you can see these are 4 compounds, and these 4 compounds can also be used as a solvent because they're low cost, but they are having very different physical chemical properties depending on the structure. So the question asks, which of the following solvents are protic, which means the hydrogen capable of forming hydrogen bonding. Aprotic. A means not protic, so which means in such organic solvent, hydrogen is not polar or positive charge enough to form hydrogen bonding. So look at the first one, acetic acid. The acetic acid is the CO double bond with OH. Apparently, this can form hydrogen bonding. So this is protic. Okay, the next one, this is also a organic solvent, a very common organic solvent. And you can see the hydrogens bond with carbon, hydrogen bond with carbon, carbon, carbon. So the hydrogen bond with carbon, that's not be able to form hydrogen bonding. Even though it have a hydrogen, it cannot form hydrogen bonding. So this is aprotic, not protic. Methylene chloride, that's also a non-aprotic because the hydrogen bond with carbon. So this is aprotic. The methyl sulfoxide. This is the organic molecule because CH structure. So you can see the hydrogen all bound with carbon. So that's not to be able to form hydrogen bonding. So this is also aprotic solvent. The protic solvent oftentimes can dissolve the ionic compound, whereas aprotic is a harder time to dissolve ionic. They all have a different use in organic chemistry, in biochemistry. Hydrogen bonding boiling point, because this is the, we've done this before, so when you see the molecule can form hydrogen bonding, then and when those molecules have similar molar mass, similar polarity, then the hydrogen bonding will stand out. It's oftentimes determined if this compound have the highest. All depends on if the hydrogen bonding is present. So you can see these 3 compounds, they are isomers, which means they have the same number of each element in the molecule. they all have 3 carbon and 9 hydrogen, 1 nitrogen. So the isomers have exactly the same molar mass. And you can see their physical properties are not quite the same. The boiling point, for example. Boiling point, this is 3.5, this is 37, this is 49. This is actually give you the highest boiling point. Very interesting, because the molecule is very similar molar mass. You would think they should behave kind of similar, but we don't see that. So why? Why does have a different boiling point? Why is the trend? Why the propylamine has highest, whereas the trimethylamine, it's interesting, this is one word, okay, trimethylamine has the lowest boiling point. You look at the molecules, we first compare the dispersion force, and then we compare dipole-dipole, and then find the hydrogen bonding. But oftentimes the boiling point, the easiest to pick, it is to find out if there's hydrogen bonding. If you see the hydrogen bonding, that oftentimes explains most of the difference. So obviously this have no hydrogen bonding, and this can have you have 1 NH bond. This molecule have 2 NH. So it looks like a more NH should have more hydrogen bonding. Is that right? So let's kind of dissect and look into the see if exactly how many hydrogen bondings they can form. And so let's make it a simple diagram. You can draw the carbon. I don't need to show them because carbon are not involved in the hydrogen bonding. I only show the hydrogen. So when you have 2 of such molecule and they can form a hydrogen bonding, here's one location from hydrogen bonding. And this hydrogen can also form hydrogen bonding with nitrogen, lone pair of the other nitrogen. So you can see each molecule can be involved in 2 hydrogen bondings. Okay. So just by looking at the structure, you would think have only 1 hydrogen bonding, but when you draw the structure, you see it's not just 1. It can form 2 hydrogen bondings because the lone pair and the hydrogen that is on nitrogen, both can form hydrogen bonding. And this molecule don't have hydrogen bonding, so we just skip that, no hydrogen bonding, because the hydrogen not bonded with nitrogen. And then you look at the last molecule, propylamine, and this molecule, how many hydrogen bondings can form from this molecule? Well, let's take a look. We kind of ran out of space. But just by looking at the this function, this part, this hydrogen should be able to form 1 hydrogen bonding with the other molecule. This hydrogen, of course, can also form another hydrogen bonding. Okay, where else in this part can form hydrogen bonding? Can anyone, any other part of this in the red circle can form hydrogen bonding?
The nitrogen.
Nitrogen, then lone pair, yes. So you have this nitrogen can form hydrogen bonding. So now you can see the difference. The propylamine have 2 hydrogen and plus lone pair can form 3 hydrogens per 1 molecule. Whereas the ethyl-methylamine, it can only have 2 hydrogen bondings. So that explains why the propylamine have a highest boiling point. And this, not so much. And of course, this trimethylamine have no hydrogen bonding, will have the lowest boiling point. So the intermolecular force, bond polarity, and they all come together, cause the difference in the physical properties. Yeah, so you are supposed to dissect into 3 different forces. Dispersion force should be similar. All across should be similar because molar mass is the same. Dipole force is hard to tell. Okay, normally we don't discuss dipole force. It's too difficult because there's so many bonds. It's complicated. We mainly focus on the hydrogen bonding because that's supposed to be the easiest to. And the location to form hydrogen bonding is just much fewer, so it's easier to spot, and they are very important. They are very powerful. So mainly focus on the hydrogen bonding when we compare the physical properties, such as boiling point, water solubility. Both have a lot to do with the hydrogen bonding. Okay, the hydrogen bonding in the molecules, we have seen that before. It's very important in the DNA, how the base pairs interact with each other. So I will skip that. Dispersion force only depends on the molar mass, but also the molecular geometry, shape of molecules. Anyway, the nature of the dispersion force, I've seen that before, is when you have a large molecules, electron travel back and forth, they can momentarily cause the molecule be polar, unbalanced. And so this unbalance will cause nearby atoms and molecules become polar, and they just briefly attract to each other, fairly weak. And dispersion force depends on molar mass because more bigger atoms, which means more electrons, they have a higher chance of electrons distribute uneven and cause stronger dispersion force. This is actually the most important. What are the factors affecting dispersion force? First of all is molar mass. And so you can see the organic molecules, the more carbon, more hydrogen, have a higher boiling point. And likewise, even for the nonpolar molecules, for the nonpolar molecules or atoms, such as noble gas, the higher molar mass causes a higher boiling point. And same with halogens. The element of halogen, fluorine, has the lowest molar mass. So the dispersion force will be the weakest. And iodine has the highest. And when you have the alcohol, even though both are polar, both can have a hydrogen bonding. This part actually the same. But the difference is this alcohol, this molecule, has fewer carbon hydrogen. And this one has more. So between these two molecules, even though they have a similar hydrogen bonding, both are polar, but a molar mass, this is bigger. It'll have higher boiling point. And in the dispersion force shape, it actually becomes important. When the molecules, even though they are isomers, have the same formula, same molar mass, and they're also all nonpolar. When the molecules have more branches, these we call them branches. It's a big chunk. These are the main, we call them stem. And when the carbon link with more than 2 carbons, we call them branched out. So we have 2 branches. So this molecule has no branch. Each carbon have no more than 2 carbons. It's all straight. And this molecule have one carbon have a bond with 3 carbons. So this you have branched out. And this last molecule have exactly same molar mass as the other 2, but have even more branches. Consider this as the main stem, the main body. You have 2 branches. This molecule, consider this, this should be the main body. You have only 1 branch. So the molecule, they actually looks different. If you go to the 3D model, this molecule looks like this. Considering the volume of hydrogen, this molecule looks like this. And this molecule looks like looks like this. The last one looks like a big fat tetrahedral. Big chunky tetrahedral. So these three molecules have all different shapes. When you have the molecule of different shapes in the pure liquid form, the packing between the molecules are different. This molecule can have a very nice, nice packing. This is almost like when you have just a whole bunch of chopsticks, and they can easily pack together very, very, very well. But between two of these molecules, the packing, it won't be very good. It's almost like when you have suppose all the chopsticks. Now you bend one of the chopstick, and you bend all of them. All the chopsticks bent, become shorter bent, kind of branch out. You have poor packing in such a case. The packing is not as packed as the others. So when the packing is not so good, the molecular contact, that will diminish the dispersion force or London force. So make the molecular attraction weaker than the close packing molecules. And you look at the last molecule. Last molecule, you have this whole molecule looks plump, very plump. And then we have this kind of plumpy molecules. The pack is even worse, even worse. And so if I use an analogy, that'll be, okay, let's say, it all depends on shape, and the shape affects the packing. It's kind of hard to find in a short moment, find a good analogy for that. But the packing affects how molecules close together. When you have molecules, CH3 branches all around tetrahedral, you don't have very close compact to each other. And that'll make the packing the poorest. And it'll actually cause a difference among the boiling point. You see this one, because the shape is very similar, like a whole bunch of chopsticks, packed very well, very tight, packed, have the strongest intermolecular force. The boiling point is highest. And this one has part of the molecule not so good packed. The packing is not too tight. Intermolecular force will be weaker. You have a lower boiling point. And the last one, because the molecule so difficult to closely pack, it makes the boiling point the lowest, because the lowest dispersion force. So that is how the shape of the molecules affect the packing, and consequently the dispersion force attract to each other. By the way, the first molecule is nonpolar. And last molecule, because symmetrical, perfectly symmetrical, is also nonpolar. The middle compound, 2-methylbutane, it is actually a not so symmetrical. The molecule, it has a small dipole, slightly polar molecule. So even though the molecule is slightly polar, because poor packing, it still makes the intermolecular force weaker than the nonpolar, closely packed molecules. And so that's the intermolecular force. The intermolecular force affects the solubility. This is actually one of the important applications. Intermolecular force and the molecular polarity both affect the solubilities. Like dissolve like, this has everyone seen that before. This If both solvent and solutes are polar, then they dissolve to each other very well. Both nonpolar dissolve very well because compatible. And in the organic molecules, there's some molecules so large, it has some polar parts. So for example, this is actually an anion come from an organic acid. And this organic compound has a very long chain, very long sticky structure that is nonpolar. And it has a small part, it is a polar because ionic charge on this oxygen. So this molecule, it has both polar and nonpolar. And when dissolving in water, the polar part will be surrounded by water molecules. And this we call a hydrophilic because they are attracted to the hydrogen of water molecules, hydrophilic. The rest of the molecule is a long chain, essentially nonpolar. That is a low polarity, we just treat as nonpolar. The nonpolar, because the polarity low, not compatible, not attracted to the hydrogen atom or oxygen atom in the water molecule. These we call them hydrophobic. They does not like water. So how does this molecule, we do use this molecule in dissolving, especially in the soap, because the when this compound dissolves in water as part of soap, the water will be surrounding the polar part through the hydrogen bonding and the ion dipole attraction. And the nonpolar part will be attracted to each other. And when there are oil and grease in the water, the nonpolar part will attract those nonpolar oils and grease and dirt. And that helps them dissolve. And the dissolving looks like this. The green part is the hydrophilic. They are surrounded by the water molecules. And the nonpolar, long chain. The long chain, they are nonpolar, attract the nonpolar oil and grease. So this is a model to explain the effect of soap. The soap is not only made of the carbon-oxygen polar group. As a matter of fact, a big part of soap in our laundry detergent come from the polar group are we call a sulfate group, or the ammonium group, positive charge. So both have a nonpolar and polar. So both can be used for detergent. Depends on what kind of the recipe they use for the detergent. So this is the end of the chapter 1. We did not get a chance to get to start chapter 2. So next week we start on chapter 2.